Hello. Now let us solve the problem. So for the first part, that is just a standard definition of continuity. So what does it mean when I say the function f is continuous at x equals to a? It means that if you calculate the limit of f of x when x goes to a, this limit exists and is equal to the value of the function f calculated at the same point a. So in other words, you can summarize this definition into this equality. So the limit of f of x when x approaches a is equal to the value of the function calculated at that point. Of course, it implicitly means this limit exists and is a number, is a finite number. F of a also is defined. F is defined at a, so it becomes a number. This becomes a number. More than that, these two numbers should be equal. In that case, we say that the function f is continuous at x equals to a. Okay, for the second part, we are supposed to calculate or actually prove that the limit of this function x squared cosine 1 over x goes to 0, exists, and of course is equal to 0. So this is what we want to prove. Okay, so if you check that, you see that you are still a little bit in trouble, because when you see that x goes to 0, 1 over x is not defined, it approaches somehow to infinity, positive infinity or negative infinity, depending in which direction x is getting close to 0. But because cosine is a finite number, even though this argument is approaching a positive or negative infinity, cosine of 1 over x is maximally 1 and minimally minus 1. So cosine is a bounded function. And x squared is, of course, a function going to 0. Okay, so you see that the standard tricks of calculating the limit will not work here. Yes? So whenever this happens, this reminds you somehow, this should remind you somehow about using a famous theorem. Sometimes it is called the sandwich theorem, or sometimes it's called the squeezing theorem. Okay, so let us just review the content of this theorem together. So assume that you have an interval I which contains the real number a. So I am using this symbol to denote that a belongs to the interval I. And let us assume that I have three functions, f, and I have g, and I have h. And assume that these functions are defined on every number in this interval I, except possibly a itself. So it doesn't matter if these functions are defined at the exact value a or not. But at any other point of this interval, all these functions should be defined. And moreover, we should also assume that the value of g at x is a number in this interval, but not equal to a. And then it should be less than or equal to the value of f at that point, and it should be equal to the value of h. It should be less than or equal to the value of h at that point. Okay, so I have an interval containing a point a, and I have three functions satisfying these inequalities at all points x in that interval, except possibly the point a itself. And moreover, we know that the limit of the function on the left, say g of x here, when x goes to a, exists. The limit of h of x, the rightmost function, when x approaches to the same number a, exists, and they are equal. Say that they are equal to the value L. What happens if all these conditions are met? Then you can conclude that the limit of the function in the middle exists, and more than that, the value is equal to L. So if I have an interval, I have three functions satisfying these inequalities on this interval at all points in I except possibly a itself, and we have these conditions for the limits of the function on the left and the limit for the function on the right, then you can immediately conclude that the limit of the function in the middle, which is squeezed or sandwiched by these two functions, exists and its value is exactly equal to the common values of that. So this means that if you have the function f is squeezed between two functions and you are lucky enough that when you calculate the limits of these two functions they happen to be the same, then immediately we can conclude that the limit of the function in the middle is also that value. But of course, if the values are different, the test is not inclusive. So it means that if this function, for example, approaches to 3, and if this function approaches to 2, you cannot conclude anything about the limits of this function. Okay, but as you will see here, this will help us because we know that, let me consider here my interval to be, for example, the open interval from -1 to 1. And then let me introduce some functions here. So for example, we know that for every value in this interval except x equals to 0 itself, the cosine of 1 over x is less than or equal to 1 and it's greater than or equal to -1. So this is valid for all x which is not equal to 0 and, for example, belongs to this interval. And then x squared is a non-negative number, so I multiply all sides of this inequality by x squared without being worried if I have to change the direction of inequalities, because x squared is non-negative. So I multiply everything by x squared and I will get that. Yes? Okay, so hopefully you agree with me. These inequalities hold for every choice of x in this interval except x equals to 0 itself, because at x equals to 0 this is not defined at all. Okay, now what I want to do, I want to give the role of function g to minus x squared, and I want to give the role of function h to x squared, and I want to give the role of function f of x to this function, and of course here my point A is exactly point 0. Okay, so what I do, I calculate the limit of the left hand side function and send x to 0. You know that this answer is 0. I calculate the limit of the right hand side function, x squared, x goes to 0, and then again the answer is 0. So this function is squeezed between these two functions. The limit for these two functions are 0, so this means that I can use the squeezing theorem and conclude that the limit of x squared cosine 1 over x, x goes to 0, is indeed equal to 0. So that is the proof for the first part, the second part of the problem. Okay? Now, for the last part of the problem, the question is that, can you find a function f so that for every x in the set of real numbers, so I am using for all, this means for all x belonging to the set of real numbers, and if the x is not equal to 0, f of x is equal to f of x, yes, and f of x, f is continuous on the whole real number r, yes. So my goal is to see if there is a function capital F so that the values of the function capital F match with the values of the function f whenever x is not equal to 0, but then the function is continuous. That is also easy to see. It is enough to define the function f of x to be equal to the limit, to the function x squared cosine 1 over x if x is not equal to 0, but 0 if x is equal to 0. Okay? let me write the function little f here also in front of you. So it is x squared according to the problem, 1 over x if x is not equal to 0, but 2 if x is equal to 0. Okay, so you immediately realize that this function is not continuous at 0. Why? Because we just learned if I calculate the limit of f of x when x goes to 0, it becomes 0, and it is not equal to f of 0, which is 2. Yes, because when I want to calculate the limit of the function when x approaches 0, this symbol means that x is very close to 0, but it also emphasizes that x is not equal to 0. That's the meaning of limit. When you are calculating the limit, you are interested in the values of the variable close to the point at which you are interested to calculate the limit, but this is clear. According to the definition of the limit, x is not equal to 0. If x is not equal to 0, the function little f follows this rule, and then in part b, we just learned that the limit of this function when x approaches 0 is equal to 0. But on the other hand, if I ask you what is f of 0, according to the definition, it is 2. So the limit is 0, but the value of the function is 2. They don't match, so this function little f is not continuous at 0. Okay, but what we have done here in definition of the capital X, I have defined this part exactly as it is here, but instead of defining it 2 when x equals to 0 as here, I defined it to be 0 at x equals to 0. First of all, I hope that you can see that the function capital F matches with function f of x for every x which is not 0. Because if x is not 0, both follow the same rule. So the values are also the same. The only difference between capital F and little f is how they are defined at point 0. One of them is defined to be 2, the other one is defined to be 0. But now if I ask you, is the function f continuous at 0, you would say yes. Why? Because if I calculate this limit, it becomes 0. If I ask you what is f of 0, it is exactly 0 again by my definition. So this function, capital F, is continuous at x equals to 0. By the way, the function f is also continuous everywhere because the only problematic point for f of x is x equals to 0. Because if x is not equal to 0, the function f of x is obeying this rule. And that's a polynomial function, and it is continuous. And if x is not equal to 0, 1 over x is also continuous, and cosine function is also continuous. So this means the composition of two continuous functions is continuous, and then if I have this one continuous and this one continuous, the product is also continuous. So this means that the capital function f is continuous everywhere, is continuous where x is not equal to 0, but also continuous if x is equal to 0. Okay? So this is the answer. So the answer to part C is yes, and the capital F of x is defined exactly as I mentioned here. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.